In this video, we'll continue looking at the second-order ODEs. From the last video, we learned the free oscillation. Free oscillation can be expressed as my double prime plus ky equals to 0. In the mechanical world, most of the oscillations are not free oscillations. There will be a damping factor. The damping can be caused by air resistance, or simply the mechanical energy is converted into heat. When considering damping, we can introduce another force term called F2, and F2 can be expressed as Cy prime. What this tells us is the damping or the resistance is a function of the speed of the object. Higher the speed, higher the damping force. Again, the total force is at 0 during the process of oscillation, so sigma f is equal to 0. What this gives us is my double prime plus cy prime plus ky equals to 0. Before proceeding further, let's introduce something called the characteristic equation. In the characteristic equation, we set y is equal to exponential to the power of lambda x. Then naturally, y prime is equal to lambda e to the power of lambda x. Y double prime is equal to lambda square e to the power lambda x. Then the original second-order differential equation can be written down as a function of lambda. At this point, we can substitute the parameters such as the mass of the object, spring constant of the spring, as well as the damping constant. I have a small mistake in my note here. The first lambda should be lambda square. Depending on the magnitude of the damping constant, we'll have three scenarios. In the first scenario, we'll have overdamping when c square is greater than 4mk. In the case of overdamping, the motion will stop before reaching half of the period. So there's no oscillation. And here is the mathematical expression to describe the overdamping scenario. In the second case, it's called critical damping. This is when c square is equal to 4mk. The motion will stop exactly at half of the period. And again, this is the mathematical expression to describe the motion. In the third case, which is also the most interesting case, when c square is less than 4mk, we'll have motion beyond half the period. In this case, we'll get oscillation. The mathematical expression that describes the oscillation can be written down as yt equals to e to the power of minus alpha t multiplied by a cos omega star t plus b sine omega star t. We can further combine the cos and sine terms because they have the same phase as well as same frequency. In this expression, c square is equal to a square plus b square, and the delta is equal to b over a. Let's just quickly revisit the first scenario where we have the overdamping case. The equation that describes the motion contains both alpha and beta. But in the critical damping and the underdamping cases, there's no more beta. This is because beta becomes pure imaginary, and beta can be written down as I omega star. Omega star, or the omega asterisk, can be written down as square root k over m minus c square over 4m square. The real part and the imaginary part of the oscillation equation is very important when you study the wave mechanics. After learning the fundamentals, we can apply what we have learned to solve real-life problems. The example we have here is taken from the previous video. The only new term it has is we introduced the additional damping constant. The value is 10 kg per second, and it is a small damping constant, and we will have damped oscillation. Here is the equation that describes the motion, and plugging the numbers, we'll have 10y double prime plus 10y prime plus 90y equals to 0. Again, let's write down the characteristic equation. We have 10 lambda squared plus 10 lambda plus 90 equals to 0. Now it's a matter of solving lambda. We get lambda equals to minus 0.5 plus minus 2.96 I. From this, we know alpha is equal to minus 0.5 and beta is equal to 2.96 I. So omega star is equal to 2.96. Based on this information, we can just simply write down the equation that describes the oscillation. We also have some initial conditions we can apply. First, the initial position is at 0, so y0 is equal to 0. That gives A is 0.16. We also know the initial velocity is equal to 0, so y prime 0 is also equal to 0. We can do a quick differentiation using the chain rule, and this is what we have. From this, we can solve B, which is equal to 0.027. The rest is trivial. And you can easily get the final answer. In the next video, we'll look at a group of slightly more complicated second-order differential equations called the Euler-Cauchy equations.